Hello everyone, welcome to this video. I am Akshay and this is the ninth video of data science series. In this video, we are going to discuss part section B of machine learning concepts of my internal test paper 2. In this video, we will cover 12 essential questions covering the fundamental concepts of machine learning. These topics are form the foundation of understanding how machines learn from data and make intelligent decisions. Whether you are preparing for exams or building a career in data science, mastering these concepts is absolutely crucial. Let's dive in. Question 11 of internal test paper 2 and question first of machine learning concepts. Transforming raw variables into more informative ones is called dash. The answer is feature engineering. Feature engineering is one of the most critical aspects of machine learning. It's the process of taking raw data and transforming it into features that help machine learning models perform better. So, what does it involve? Creating new features from existing ones, selecting relevant features, scaling and normalizing data, handling missing values, creating polynomial features. So, let's take a real world example of feature engineering. If you have a date of birth, you might engineer it into age, which is more useful for prediction. Or you might create month from a date to capture seasonal patterns. Why is it important? Better features lead to better model performance, can reduce training time significantly, helps the model understand patterns better, often more important than the algorithm choice itself. Experienced data scientists spend 60 to 80% of their time on feature engineering because it directly impacts model success. So let's proceed to question 12. Numeric data types. Uh, so this question is about predicting a numeric value such as salary is an example of dash. The answer is regression here. When you target variable when a target variable is a continuous numeric value, you are dealing with a regression problem. Key characteristics of regression. Output is a continuous number. Examples salary, price, temperature, weight. Their goal is to predict the exact value. Comparison with classification. Regression predicts continuous values. Classification predicts categories. Which category? Common regression algorithms. Linear regression, simple and interpretable. Polynomial regression for nonlinear relationships. Ridge, lasso regression with regularization. Support vector regression for complex patterns. Let's see some of the real examples. Predicting house prices, we use regression. In predicting CGPA, we use regression. In predicting GPA, we use regression. In forecasting sales, we use regression. Understanding whether your problem is regression or classification is the first step to choosing the right approach. So let's proceed to question third. Model performance issues. Let's read the question first. A model that fits training data perfectly but fails on new data suffers from dash. The answer is overfitting. So let's see what is overfitting. Overfitting is one of the most common problems in machine learning. It happens when your model learns the training data too well, including its noise and peculiarities, rather than learning the underlying patterns. So let's see what causes overfitting. Model is too complex for the data. If there's too much training time, if there's not enough data, or if there's no regularization. Signs of overfitting: very high accuracy on training data, much lower accuracy on test data, large gap between train and test performance. Let's see how to prevent it. Use simpler models. Use regularization like L1, L2. We also could use cross validation, more training data, and early stopping. So let's see its analogy. If you memorize all answers to past exam questions without understanding concept, you'll fail new problems. That's overlifting. So now let's proceed to question fourth. Uh, Question fourth is about regularization techniques. Let's read the question first. Dropout and weight penalties are examples of dash methods. Here, the answer is regularization. Regularization techniques are used to prevent overfitting by constraining the model's complexity. Let's see some common regularization methods. L1 regularization, lasso, which is also known as lasso, adds penalty for feature weights. L2 regularization, ridge, adds penalty for squared with feature weights. Drop out, randomly removes neurons during training. And last one is early stopping. Stop training when validation performance plateaus. So let's see how they work. They add a penalty term to the loss function that discourages the model from becoming too complex. So let's look at example of regularization. Without regularization, model learns every detail, including noise. With regularization, model learn only important patterns, and we only want our model to learn the specific and important patterns. So that's why regularization is important. Why it matters: improves generalization to new data, creates simpler, more interpretable models, prevents the model from overfitting, makes training and more stable. In neural networks, dropout randomly deactivate neurons, preventing co-adaptation. Weights penalty discourages extreme weight values. Let's see our next question, which is about ensemble learning. Let's read the question. Training multiple diverse models to improve accuracy is known as desk learning. The answer here is ensemble. So let's look at ensemble. Ensemble learning combines multiple models to achieve better performance than any single model alone. This is based on the wisdom of crowds principle. How learning works. Let's see how it works. Instead of relying on one model, you train multiple models and combine their predictions. This diversity leads to better overall performance. Let's look at some of the popular ensemble methods. First one is bagging. It includes bootstrap samples, train independent models. Its example is random forest. Second method is boosting, sequential models where each learns from previous mistakes. Example is gradient boosting, XGBoost. Third one is stacking, combine predictions from multiple models as input to a meta model. Let's see why ensemble is effective. Because it includes different models, catch different patterns, reduces individual model errors, more robust to outliers, typically wins competitions. Real world impact of ensemble. Netflix prize winners use ensemble methods. Kaggle competition winners almost use ensembles. Outperformers individual models by 10-20% on average. Ensemble methods are one of the most powerful techniques in machine learning.